Swayam Prabha. Digital India. Educated India.
In this lecture, we are going to look at the impulse momentum relations for planar kinetics of rigid bodies. We will look at the impulse momentum relations which are derived from the equations of motion for planar kinetics of rigid bodies, and finally look at the conservation of momentum. We are also going to take up some problems. Now, we start with the equations of motion about the center. The angular momentum equations are written about the center of mass. The first equation, which is the linear momentum equation, Newton's second law for the center of mass, states that the rate of change of linear momentum of the center of mass is summation of all forces acting on the body, and the rate of change of angular momentum about g is the net moment of all forces about the center of mass. This can include couple moments as well. If I integrate these equations over time, first the linear momentum equation, I get the change in linear momentum on the left hand side equal to the impulse of the force from the right hand side. If I look at two time instants over which I apply this, I get the linear impulse momentum relation. If I integrate the second equation, which is the angular momentum equation, I get the change of angular momentum in terms of the angular impulse. If you write down the equation of motion about a point P which is fixed, this is a situation that arises very commonly. We have the equations of planar kinetics for the linear momentum of the center of mass and the angular momentum, relative angular momentum about P. Here, because P is a fixed point, therefore, acceleration of P is 0. We have a simplification, and the expression of angular momentum, relative angular momentum about P, is given by this expression. The first term is the angular momentum because of the motion of center of mass with all the mass concentrated there. We have the momentum, which is rho g prime vector, which goes from P to G in the figure, across the linear momentum of the center of mass with respect to the point P. The second term, which is written under the integral, it is the angular momentum about the center of mass, and these expressions we have seen many times before. For a rigid body, I can write this linear velocity. This is nothing but velocity of center of mass. This rho g prime dot is nothing but the velocity of center of mass. That is essentially the relative velocity of center of mass with respect to P, but because P is a fixed point, that becomes velocity of center of mass. And we have used these expressions that rho dot is omega cross rho and rho g prime dot is omega cross rho g prime vector. These are used here and here, and using these expressions and considering that we are dealing with planar kinetics, I express the position vector of the center of mass in the Cartesian coordinates, and if I plug in all these expressions in here, I will get from the first term mass times rho g x square plus rho g, this is rho g x prime square, rho g y prime square. This is nothing but the magnitude of rho g prime vector square plus the integral gives us I g times omega. I have pulled out omega. The first term also will give me omega, the second term will also give me omega, that I have pulled out. What is there in the square brackets is nothing but moment of inertia about g plus mass of the body times the distance square, and therefore, this bracketed quantity is nothing but moment of inertia about p, moment of inertia of the body about p, and that is the expression of h p rel. Therefore, h p rel gets considerably simplified because of this planar motion assumption, and this is this can be written for prismatic bodies. We are discussing prismatic bodies. Thus, we have h p rel dot as net moment about p, and h p rel expression is nothing but I p, the moment of inertia about p, times the angular velocity, which is in the k cap direction. K cap is perpendicular to the plane of the screen. Integrating over time, I get the change in the angular momentum about p is equal to the impulse of all forces, impulse of the angular impulse of all forces about p, and this moment about p can include couple moments. Therefore, this is the angular impulse about p. The net angular impulse about p is equal to the change in angular momentum about p. Now, we come to conservation of momentum. If the net force on a rigid body is 0, then the linear momentum of its center of mass is conserved. This follows from the linear momentum equation, which we found we derived from Newton's second law. So, this is Newton's second law for the center of mass. This is our linear momentum equation. If I integrate that, and if I find that there is no impulse on the right hand side where I have the impulse integration of the force, if there is no net force, then it tells us that the linear momentum of the center of mass is conserved. If the net moment about the center of mass of a rigid body is 0, the angular momentum about the center of mass is conserved. Follows from the angular momentum equation about the center of mass, which we had integrated, and if there is no angular impulse, there is no moment acting on the center of mass, net moment acting on the center of mass, then the angular moment the angular impulse goes to 0, then we find from the left hand side that the angular momentum about the center of mass is conserved. If the net moment is 0 about a fixed point in inertial space or a fixed axis about which the body undergoes fixed axis rotation, then the angular momentum about the fixed point or fixed axis is 0. We are going to look at some problems. This is again sourced from the book of Merriam and Craig Dynamics. This says a uniform slender bar of mass m, capital M, and length L is translating on a smooth horizontal xy plane with velocity v, capital M. When a particle of mass lowercase m travelling with velocity v sub m perpendicular to the bar strikes the bar at the location shown and becomes embedded in it. Determine the final linear and angular velocities of the bar with its embedded particle. Here in the figure, we see that this bar is travelling in the x axis direction with a velocity v sub capital M, and this particle is about to strike. Even though I have shown a gap between the particle and the bar, it strikes at L/4 from this farther end. Therefore, this particle is striking this bar, this gets embedded in the bar at L/4 from the farther end of the bar. There are no external forces, the horizontal surface is frictionless, there is no external forces on the whole system. Of course, when this small m gets embedded, there will be an impulsive force, but that is internal to the system. There is no external force on this system. Therefore, the net linear momentum of the center of mass of the whole system will be conserved, and the net angular momentum about the center of mass of the whole system will be conserved. Therefore, we have to find out the center of mass first. This is the first task, and here I have done this. You notice that G sub capital B is the center of mass of the bar, which is midway, the bar is uniform and slender. Therefore, G sub B is at the center of the bar. Capital G is the center of mass of the combined system, which is the bar and the particle. Capital G point is the center of mass of the combined system, and I can find out this distance d that I have marked here. This I can find out by using the center of mass relation. This d is found to be mass of the particle times length of the bar divided by 4 times the total mass. This can be easily found. Next, I start writing the linear momentum conservation. First term is the linear momentum of the bar before the collision occurs. So, left hand side is the linear momentum before the collision occurs. The bar was moving with velocity v sub capital M along the I cap direction, and the particle was moving with velocity v sub small m in the j cap direction. I have written out the linear momenta of these two objects. One is, the first term is for the bar, the second term is for the particle. On the right hand side, I have the linear momentum of the center of mass of the whole system. This is after the particle gets embedded in the bar, and from here I can find out the velocity of center of mass of the whole system. Capital M is specified, its velocity is specified, everything is known on the right hand side. So, we know the velocity of center of mass of the bar. Let us now go over to conservation of angular momentum about the center of mass. I have to calculate the angular momentum of the initial angular momentum of the particle and the bar about the center of mass of the whole system after the particle gets embedded in the bar. If you look at the initial angular momentum of the bar itself, then it is 0, because the velocity of the bar v m before the impact takes place, the moment arm about g is 0. Therefore, the angular momentum contribution from the bar's motion is 0. But there is a contribution of angular momentum before the collision. There is an angular momentum contribution of the particle about the center of mass which is going to form, because we have to conserve the angular momentum about the center of mass of the whole system. The angular momentum conservation, the angular momentum contribution of the particle about the center of motion mass of the whole system, which is g, is given by the arm. Arm is this vector. this is the arm, and this arm is nothing but this is L by 4. Therefore, this arm becomes L by 4 minus d in the I cap direction. L by 4 minus d, this is the arm cross linear momentum of the particle, which is m times v sub small m j cap. This is the angular momentum contribution of the particle before the collision about the center of mass of the whole system, and that must be equal to the moment of inertia about the center of mass of the whole system, because now the particle has embedded in the bar. I have to calculate the moment of inertia of the whole system about g, and that times the angular velocity of the whole system after the collision. Let us look at this calculation then. Moment of inertia about g is now for the bar, it is m L square by 12 about its center of mass plus parallaxis theorem, it shifts by a distance d, therefore, plus m of the bar distance square, plus the last term is the contribution from the particle. So, mass of the particle times the distance from the center of mass whole square. So, that gives me the moment of inertia of the whole system, the bar particle system about the center of mass of the whole system. So, if you simplify, this turns out to be this expression. Now, this is what I am going to substitute in my relation and straightforward algebra. Leave it to you to say to find out the angular velocity. So, this is what I get as the angular velocity of the whole system, the bar with the particle embedded in it. This is the angular velocity of the system. Now, because you know the linear velocity of the center of mass and angular velocity of the bar, you can find out velocity of any point on the bar. We move to the second problem. This is taken from the Merriam-Craig's book of dynamics. Determine the minimum velocity v which the wheel must have to just roll over the obstruction. The centroidal radius of gyration of the wheel is k, and it is assumed that the wheel does not slip or leave contact. This is a common problem we encounter, that a wheel while rolling hits a curb, and this is the curb height h. Here there is this assumption, if the curb height is not too large and the mass of the wheel is quite high, then this wheel is not going to or the velocities are low, this wheel is not going to slip or jump. Therefore, we are working under this assumption that the wheel after hitting the curb just rolls over. There is no slipping at that corner or no jumping of the wheel, no loss of contact. We consider the system and this corner point A, and this point A is assumed to be the rollover point. Now, when the wheel hits this corner, there will of course be an impulsive force that acts at the corner on the wheel, at the contact point on the wheel. Now, because this is an impulsive force at that corner, if I consider the angular momentum of the system at about that point, then there is no other impulsive force. If I consider the angular momentum about that point of contact with the corner A, then there are no other impulsive forces. Therefore, angular momentum of the wheel about that point just before the collision and just after the collision will be the same. The angular momentum will remain same just before the collision and just after the collision about that point. Therefore, angular momentum conservation about A is that contact point on the wheel where it contacts the wheel. We have angular momentum conservation about that point. Therefore, we must have angular momentum of the wheel before the impact at A must be equal to the angular momentum of the wheel just after impact about the point A. We will calculate the angular momentum before the impact. The wheel was moving, its center of mass has this velocity and it also has this angular velocity, and remember that angular momentum is the contribution of the angular momentum because of the motion of center of mass and angular momentum because of the rotation about the center of mass. Therefore, my angular momentum expression before impact has two contributions. The first one is because of the angular momentum of rotation about the center of mass, I g in moment of inertia about the center of mass times the angular velocity of the wheel, plus this is because of the translation of center of mass. A g is of course the center of mass. When it has hit this point, A g is that vector when it has hit just before it hits. This picture is just before it hits, and you can consider it just after it hits. So, the wheel hardly has time to move in that very small time interval over which we are integrating the equation of motion to get this impulse momentum relation. Okay. Therefore, the first term is the angular momentum because of the rotation about the center of mass, and the second term is the angular momentum because of the translation of the center of mass. A g is the moment arm times mass of the wheel times velocity of the center of mass. That is the total angular momentum about that contact point A just before the impact, and if you plug in all these values, I g is the determined terms of the radius of gyration, and I have taken this z axis is moving out of the plane of the screen. Because of this velocity in the positive x direction, we must have angular velocity as minus V g by r in the k cap direction. So, this is our angular velocity vector minus V g by radius of the wheel k cap, and to that I multiply m k square, which gives me the moment of inertia about the center of mass. A g vector I can represent, and I take the cross product, and finally I get this expression. You can very easily see that this perpendicular distance is r minus h. Therefore, mass of the disc times velocity of center of mass times this perpendicular distance k cap, and with a negative sign when you take the cross product, that will give you the angular momentum about point A because of the motion of center of mass. Next, I calculate the angular momentum about point A just after the impact, when the wheel starts rolling over point A. The same picture with the red circle suffices, angular momentum now will be, because it is rolling over this point A, I can assume that it is hinged at A. Therefore, the angular momentum is the moment of inertia about A times the angular velocity just after the impact, which I write as omega prime k cap. I will find out omega prime. Plugging in all these expressions and using the angular momentum conservation, finally I obtain omega prime, the angular velocity of the disk just after it hits A, just after it hits A. Now, with this angular velocity it starts rolling over point A. Now, when it starts rolling over, it starts with this angular velocity, but as it rolls over it gains gravitational potential energy. Let us see what happens then. Since it is rotating about that fixed point A and there is no other active force other than the weight, which is a potential force, total mechanical energy of the system will be conserved between these two states. What are these two states? One is just after it has hit the corner, and so this is the starting state. Here I know omega prime, and finally what will happen, this wheel will climb up. In contact with that corner A. I consider these two as the two states of the system. Initially, I have considered the datum, potential energy datum, as this center. Therefore, this is V equal to 0. Initially, in the state 1, which is the red circle, the potential energy is 0, but there is a kinetic energy contribution, that is T1. In state 2, if we have to find out the minimum starting velocity V, this is where it comes to rest. Therefore, the kinetic energy in state 2 goes to 0, it just about climbs the curve. Plus potential energy. Potential energy is because of this change in height, which is h, change in height of the center of mass of the wheel, and that is h. Let us proceed with this calculation then. We know that the kinetic energy can be written as half I A omega prime square. It's hinged, considered to be hinged at A. Therefore, I can write kinetic energy as half I A omega prime square. This is in state 1, and that is equal to the net potential energy in state 2. The whole kinetic energy is getting converted to potential energy, and that is mgh. If I substitute that expression of omega prime that I have determined in the first step in here, I will do these algebraic steps, and finally we can determine Vg, the minimum velocity of center of mass required to just climb the step. So, that completes this problem. So, to summarize, we have looked at the impulse momentum formulation for plane kinetics of rigid bodies. We have derived the linear impulse momentum relation and the angular impulse momentum relation. We have looked at some problems and shown how conservation of linear and angular momentum, they are used in problems. With that, I will close this lecture.